All right, we're going to review nomenclature because it does pertain to what we're getting ready to do. So, first thing, you're going to name the first element or ion, because it's first, it's the cation, which is the positively charged ion, followed by the second element or ion. If it's the second ion, it would be the anion. It's negatively charged. Change the ending of the second element or ion to "-ide", unless it's a polyatomic ion. And rule 3 switches depending on which type it is. So you need to be able to identify ionic compounds versus covalent. The ionic compounds is a conditional statement, if the metallic cation. This tells us a few things. Number one, it has to be first. It cannot be the second thing. It has to be first. It's the cation. Second, it has to be a metallic cation. There is a polyatomic ion, ammonium, which is positive and therefore can come first. But it cannot get what is happening here, which would be Roman numerals. The next thing is it has to have multiple oxidation states, which will be interpreted as charges for this. All charges are oxidation states, but not all oxidation states are charges. It's kind of like all squares are rectangles, but not all rectangles are squares. But you're going to have to figure out which Roman numeral to use, and it is going to indicate the charge that is used. So a positive 1 charge gets a Roman numeral 1. A positive 3 charge would get a Roman numeral 3, which is 3 capital I's. Again, it's conditional, so it doesn't always happen. With covalent compounds, you do need to do this. There are some little issues. They're shown in the smaller font there. But you're going to add Greek numeric prefixes to indicate the subscripted value for the first and the second element. The first element can never have mono. Now, there can be one of that thing, but you're not going to put down mono. Think of it. Monocarbon dioxide, monocarbon monoxide. Sounds a little strange. Carbon dioxide, carbon monoxide. Sounds fine. Now, by choosing those two, I also indicated the next part. If a numeric prefix ends with an A or an O, like mono does, and it's accompanying oxygen, typically in the oxide form, then you're going to drop the A or the O from the prefix. So, carbon monoxide, not carbon monoxide. The other thing is carbon dioxide. Nobody dropped an I just because the I and the O were next to each other. Let's go ahead and give this a little bit of practice. Right here we have phosphorus and we have sulfur. We're going to go ahead and take a look at this. I notice that the second one is not a polyatomic ion, so we're going to go ahead and erase the ending here. Sometimes it's hard to tell where that ending needs to change. We're going to change it to sulfide. Next thing, we're going to go ahead and take a look and see that this is phosphorus and sulfur. Both of them are nonmetals. Not a single one of them could give us a Roman numeral. So we're going to go ahead and add our Greek numeric prefixes. So diphosphorus. Hopefully I gave myself enough space. Pentasulfide. I'm going to go ahead and click Show Answer. And it's going to tell us that, yes, I did in fact get it right. Go ahead and do a new problem. Okay, we have silicon, and we have sulfur again. By now you're like, hey, sulfur is not a polyatomic ion. I'm going to go ahead and jump the gun and get this "-ide" ending in there quick. Now, silicon is a metalloid, a semi-metal. It's one of the ones that's on that staircase on the periodic table. It's a little iffy. It could become ionic, it could become covalent. This one is going to probably lean towards being labeled as covalent. So we're going to add those Greek numeric prefixes. mono does not get added in, but the second one always gets one no matter what. So the di prefix definitely goes in. And so there we go, we've got that. All right, here we go with one with a lot of stuff. Now, as soon as I see 3 or more things, I know that a polyatomic ion is involved. I should get my polyatomic ion sheet out. So I'm going to go ahead and name the first, followed by the second. So I need to know where my first and my second are. Unless the first is ammonium, NH4 with a +1 charge, the first one is going to be a metal. The rest of it has to be my second portion. So this is strontium. And then that second portion, go to your polyatomic ion sheet, take a look. Oxalate. This is where we get a chance to see that the second step does not happen for the polyatomic ions because it already has its own special ending that I cannot disturb. And then the final step, step 3, is a conditional one for the ionic ones. Strontium is in either the first or the second column of metals and therefore is guaranteed to not have a Roman numeral. So I'm in the clear. I don't have to do anything. This is going to give me the proper name. So there we go, strontium oxalate. All right, let's go ahead and take a look at it going the other way around. All right, so let's go ahead and go from a name to a formula. This tends to be easier. For this, you're going to write the element or polyatomic ion symbol for the first element or ion, the cation, followed by the element or polyatomic ion symbol for the second element or ion. And if it is the second ion, then it is the anion. Now for this, you're going to have to know if it is ionic or covalent. And so a lot of people, how do I know? Practice, lots of practice. But here's the thing, ask yourself a few simple questions. Does it start with a metal? If so, it's ionic. Are there 3 or more element types shown? If so, it's ionic, since there's a polyatomic ion present. And unless it starts with NH4, you're going to start with a metal still. So that first rule would still kick in, that first question would still kick in. Is there a Roman numeral? Check out your name. Is there a Roman numeral in the name? Okay, so if there is, then hey, you're in good shape. Now, as far as the 3 or more element types, you might not be able to tell because, again, you don't have the formula actually written out for you. But does it end with ite, I-T-E? Does it end with ate, A-T-E? That's going to indicate that you've got that going on. The ammonium is one that you're going to also have to try and remember. Now for ionic, you've got your symbols. So you're going to go ahead and label the ion of each with its appropriate charge. And then you're going to ignore the sign of the charge, plus or minus, doesn't matter. And you're going to crisscross those charges down to subscripts for the opposite ion and reduce to the simplest whole number ratio of those things present. That means the math was done for you very, very quickly. If it's covalent, well, everything's kind of labeled out there for you because if you know your Greek numeric prefixes, or at least have a list to look at, it's pretty easy to look at them and say, aha, tetra, well, that means there's 4 of something. Penta, ooh, there's 5 of that thing. Hexa, oh, there's 6. Mono, ooh, there's 1. Oh, it's not listed. It must be mono. There's just 1 of that. So you're going to go ahead and take those Greek numeric prefixes and write the meaning of that prefix down as the subscripted amount for the respective element. Again, let's go ahead and take a look at that. So here's one that looks a lot like the last practice one that we did. We've got that silicon in there, so here we go. Let's go ahead and jot down its symbol. And selenium, there's its symbol. We can already sort of look for those prefixes and we're like, hey, there's going to be 2 of the seleniums. So maybe I did that as rough draft work and now I can push them together a little closer. Remember, capitalization does matter. Go ahead and click Show Answer. This one, sodium nitrate, it ends with an ATE. I know that this is going to be a polyatomic ion. It also starts with sodium, which is in the first two columns of metals, which tells me it's a metal. And so I go ahead and I look it up, and I'm already going to jump ahead and say, look, I need to write down its charge. With nitrate, I go to my polyatomic ion sheet. I jot that down, NO3 with a -1 charge. The crisscrossing and reducing, ignore the signs, but crisscross, you need 1 nitrate for every 1 sodium. So NaNO3. Now if I had needed more than 1 of the polyatomic ion, then it would go in parentheses, and I would put the number needed outside of it. But if there's only 1 of it, everyone that has a clue, an inkling, knowledge of this chemically is going to end up putting down NO3 and knowing that that was nitrate. They don't need anything extra. On to reviewing empirical formulas. The reason we can name things as systematically as we can is because of the experimentation that came before that showed consistent ratios. Our balanced chemical formulas, CO2, NaNO3, Si, Se2, all of those things came from just consistent ratios that they were seeing, and similar physical and chemical properties that were observed through experimentation. Unfortunately, we can get a little bit cocky, so I do want to go back and take a look at these steps for determining an empirical formula, and then I'm going to show you an example that you'll look at it and you'll say, well, if I know my nomenclature, then I don't need to do this math work. I already know this. Well, you only know it because somebody else did all the hard work, and you need to remember that you might also have to do the hard work. So first, determine your sample size. If it's not already given, we can hope that you were given percent composition instead, and then it's advisable to assume a 100 gram sample because you can just turn the percent signs into grams and away you go. Now percentages and mass amounts are not good ratios. They just tell you, hey, you've got some of this thing. They don't tell you an amount, like a quantity of that thing. And so we want to get to quantities. Our ratios are based off of the quantities of the atoms present. So the quickest way to do that is to determine the moles of each element present. You'll need the molar mass for each element in order to do this. Now once you do that, your mole to mole ratio is actually a true quantity ratio. It's just not a very good one, most likely. So you're going to want to both clean and polish it up. To clean it, divide all mole amounts by the smallest mole amount determined. That should give you a fairly clean ratio, hopefully very clean. You're then going to go ahead and polish it. You're going to ask yourself, can all of the values now be rounded up or down to whole numbers? The only ones that are allowed to be rounded are going to be ones that are within 1/10 of a whole number. All others you're going to need to multiply by a common multiplier that would allow that to then be true. And so here are the 3 or 4 rather other options that we've got. If you see something ending with a half, then double it, 2 halves in every 1 whole. Or thirds, 1/3, 2/3, triple them. Quarters, quadruple them. Fifths, quintuple them. Make sure that your values need to be multiplied by what they need to be multiplied by. If you think that they need to be multiplied by something that is greater than 5, you've probably made a rounding error mistake somewhere along the lines. So let's go ahead and try this once. So I've got a calcium and chlorine compound. Here's where that cocky person comes in. That cocky person says, well, it's got calcium. Well, I know that's got a +2 charge. It's got chlorine. Well, this is clearly ionic. That's got a -1 charge. I'll go ahead and crisscross, and voila, here is your formula. Now, an empirical formula is the simplest whole number ratio of all atoms present. An ionic compound, a formula unit, is the simplest whole number ratio of ions present. The ions here are 2 separate elements, calcium and chlorine, and so the empirical formula and the actual formula line up pretty easily with these things. So some people are like, but I already have it. I have the answer. Okay, well, let's do it the long way. Let's go ahead and do it the empirical formulas way, because we're going to hit a point where we're not able to do it any other way. So let's go ahead and take our percentages and assume a 100 gram sample, which gives me 36.03 grams of calcium, 63.96 grams of chlorine. I'm going to go ahead and divide both of them by their respective molar masses that I can get off the periodic table. And doing this is going to allow me to have an actual quantity in mole amounts for each of these things. I'm going to hold on to a few digits. So we're going to go out a little bit. And it says I've got this many moles of calcium using this sample size, and this many moles of chlorine using this sample size. Now, this to this is a true mole ratio. It is a quantity ratio. It's just rather ugly. So let's clean it up. Let's go ahead and divide both of them by this smallest amount. So we're going to take the smallest one and divide it by itself, and that's going to tell me that I have 1 calcium in this ratio. I'm going to take the other one, the chlorine, and I'm going to go ahead and divide it by the smallest mole amount. Notice I'm not including the unit or label calcium. The reason I'm not doing that is I want to see moles go away and just leave me with a number of these things. And so when I do this, I get 2.0068. 0.0. Am I within a tenth of a whole number? Yes. So I'm going to go ahead and round to 2. And so I can state that this is the empirical formula. And again, somebody's going to say, but hey, I already knew how to do that. I know nomenclature. Well, good for you. What happens when we get to the covalent compounds and we use those Greek numeric prefixes and didn't feel like there was much of a rhyme or reason for why everything went together? And so now we're taking a look at 4 polyatomic ions, all featuring chlorine and oxygen, and every single one of them is in the -1 charge area of our polyatomic ion sheet. Every one of them. How is this possible? How are they stable enough that they manage to have the exact same charge, and yet here they are? So, valence shell electron pair repulsion, which is what we're moving on to, what Ms. Smith and Mrs. Deshane have been providing you with information on, with videos and various things. We want to be able to draw these structures, build these structures, and know why they are the way they are, because it's going to give us some unique properties. So with this, we're going to go ahead and we're going to look up chlorine and oxygen, and we're going to find them on the periodic table, and we're actually going to do something rather simple. We're just going to count over the number of columns, the S and P block sections, skip the D, the transition metal section. Count over how many electrons do each of them have on their outside, on the valence area. Well, each chlorine is going to have 7, and each oxygen is going to have 6. So what we're going to do, and I'm going to do this first one, what we're going to go ahead and do is say, look, you've got 7 electrons coming from chlorine and 6 coming from oxygen, and this -1 charge, we're going to go ahead and give you 1 extra electron because clearly it came from somewhere. Where? Not sure, don't know what the cation is that gave it to him. But that gives us 14 electrons to work with. We're then going to go ahead and choose one of our elements to be the center atom. This is typically the one that's all by his lonesome. I can look at the other 3 ions and say, ooh, we're going to say that chlorine is in the center. We're going to go ahead and put the other things, in this case the oxygen, equidistant around that thing. We're then going to go ahead and start making bonds. each bond is a shared pair of electrons, and so it counts as 2 electrons. So look, there's a bond between chlorine and oxygen. That is going to use up 2 of these 14 electrons. It's going to give us 12 left to use. We're then going to go ahead to the outside one and start adding on lone pairs. Notice they're always in pairs. Lone pairs of electrons to the oxygen or whatever's on the outside until we reach our octet, which would mean that it has 8 outermost electrons. So the bonded pair and then these guys, they all count as having a total of 8. And we're like, yay, he's probably happy. So we have now used up 6 more of those electrons, and we've got 6 left to use. I'm going to go ahead and put the leftovers in lone pairs around the central atom. And so now we've used up all 6, and again, chlorine is probably pretty content because it's got 2, 4, 6, and 8 electrons. Now we might think, we did a great job, we did a terrific job. I'm glad we did such a good job. Do we know we did the best job? Well, this is where something called formal charge comes in. You'd like to have a formal charge as close to 0 as possible. So we're going to go ahead and we're going to solve that for each of our elements. Now, if an element occurs bonded the exact same way, you only need to solve it once. But if it gets bonded 2 or more ways, then you're going to have to show it each and every way that it happens. So right here, it's pretty easy. We've got a chlorine and we've got an oxygen example. So first thing, let's go back here. Hey, we said that these had 7 valence electrons that we could use up. Okay, we're now going to subtract the electrons that were used. We're going to go ahead and subtract every bond that we see, so every line that we see, and every lone electron that we see. So 1, 2, 3, 4, 5, 6. And so 7 minus 7 is 0. He's pretty happy. All right. With the oxygen, 6 valence electrons. I see 1 bond right here. So there's that. And 1, 2, 3, 4, 5, 6. 6 electrons. 6 minus 7 is -1. Well, hey, looky here. It's not a formal charge of 0, but is it going to be content? Absolutely, because it shows us where that bonding is going to take place when this polyatomic ion attaches to anything else. It also allows us to remember that oxygen typically favors making 2 bonds, and so this oxygen is open to making a second bond with something else. Let's go ahead and try it with one of the other ones. Let's go ahead and try it with this next one. This time we're going to double our amount of oxygen electrons. So we have chlorine in the center, 2 oxygens equidistant on the outside. And how many electrons do we have to use? Well, we had 7 and this twice, so 12. And hey, there's that guy, the -1. And so we have 20 electrons that we can use. So 2, 4 just got used up in bonding. So we used up 4. Got 16 left to use. Go ahead and sprinkle those around as lone pairs. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I've used up 12. Remember, I only want to hit that octet rule. So I've got 4 electrons left. I'm going to go ahead and, oops, that looks awfully close together. We're going to just make that one a little fatter looking. And go ahead and put the 4 other electrons on there, on the chlorine. Okay, well, let's check its formal charge. Okay, so 7 minus, I see 2 bonds, 1 here, and 4 electrons equals 6. 7 minus 6 is 1. Ooh, not a formal charge of 0. Okay, currently both oxygens are bonded the same way. 6 valence electrons each, minus, I see 1 bond on this guy, and 1, 2, 3, 4, 5, 6. 6 valence electrons. So 6 minus 7 is -1. So right now I've got a -1, a +1, and a -1. If I could make 2 of these into zeros, I would be much, much happier, much more stable. And so we're going to go ahead and we're going to steal one of these lone pairs. We're going to steal this guy, and we're just going to turn it into another bond. By doing this, we now have 3 bonds off of this chlorine. I still see the 4 lone electrons. 7 minus 7 is 0. So he is now 0 for a formal charge. That's nice. This oxygen is still like this. Let's leave him alone. Let's try out the other oxygen. 6 valence electrons. He's got 2 bonds happening, and 1, 2, 3, 4, just 4 lone electrons. Remember, this one right here, stolen, turned into a shared pair there. 6 minus 6 is 0, a formal charge of 0. And so we're going to rewrite this. So we're going to go ahead and redraw this as Cl with our bonds to oxygen like this, and our lone pairs like this. And he still has that -1 charge hanging out over here, and so this is also again drawn much, much better.